Okay, awesome. So welcome to the session on the interface between control electronics and the runtime. So this is a little bit of a change of topic from the morning session that focuses mostly on architecture. So what do we expect from today's session? So we are in the newest working group within openQSE. And the concepts, ideas that we're going to show here today are based on discussions that we had with some of the people. Like we realized that there was a need to have sort of like this common language between the hardware and control electronics. And they are just a seed to the discussion, like nothing is like set in stone. So please make the session as interactive as possible. Like I didn't prepare like a lively talks or like topics per se, but it was more of like kicking up the discussion as to what can be achieved within openQSE. If you don't know me, I used to work at Oak Ridge. I work at Qblocks now, so we do control electronics. It's one of the few vendors in the market. So today, I'm not wearing my Qblocks hat. I'm gonna try to keep the discussion as vendor agnostic as possible, but most of the stuff that I learned, because this is not my background, like I used to do scientific computing, is based on that perspective. And again, I would like to encourage you to just stay engaged. Also, we have a few people online, so if you are asking a question, I would like to ask you to please like say your name and perhaps your affiliation, so we can all like stay engaged. We have mostly the same number of people online than here, so please be mindful of that. Um, I think that's it for baseline housekeeping. And I thought I would start by giving you like a one-on-one overview of quantum control, because I feel like from most of the diagrams that I've seen today, most people see like this sort of like black box of a quantum computer. So you have like a user that is interacting like to sending instructions to like a quantum device. And again, I'm gonna be a little bit biased to superconducting qubits because that's my background mostly, but of course we would like to encourage people from other technologies to chip in. So again, if we open up like this sort of like black box, you realize that there is more than the actual like chip. You have like the fridge, you have the cables that go from like the fridge to the chip, and then you have the control stack. But also the control stack, it's not like a standalone box, black box. There's many interfaces that go into there. And before I dive into what this interface is and sort of like data transfer looks like, if you're not aware of like what our role within the control stack is basically we make sure that your algorithms run as you would expect them to run. So if you see like on the diagram to the right, that's what you will expect to see. So you send your BQE, you send your machine learning algorithm, you want to run it for like multiple shots and you want to run it like every single time the same. So the control stack like really makes sure that that happens. And also, there are some cool hardware features that as an end user, I guess you don't really see, like beyond just like asking for like a number of shots to make sure that your qubit is calibrated. There are some features that you could actually, I guess, enable or access if you have enough exposure from the control stack to access these features. And just to give you an idea of like the latency, so this is how long it takes at the control stack to run all of this. And it's really hard to see, I know. It looks good on my screen, but not in here. So these are sort of like the tasks that run within.
Is it possible to use the toggle chat? Yeah. Make sure. It's okay.
So everything that you see on like the lower left corner are sort of like the reflexes, like things that happen like on real time on the hardware, and then you can sort of like use them as the ingredients for your recipe to build your variational algorithm, your calibration scheme. And this is sort of also to give you an idea of like how wide this latency like spectrum we're talking about, and also to like anchor this discussion about perhaps later set up terminology about what we mean about real time, near time, because control is everything about how fast you can do it and like how often can you do it. So this is gonna be even more difficult. So this is basically the data flow that goes in and out of the control stack. So the gray box that you see on the middle is what lives inside the control stack. And here it is color coded and shape coded. So basically, if it's a circle, it's a process. If it's a rectangle, it means it's data that on this particular diagram, it could be updated, or it could be like static. And it's color coded to include NISQ sort of applications in pink and QEC workflows on green. So if I walk you through here, I also can see, but basically it starts with the user deciding on the task to be run. Then the control stack takes as an input sort of like all the qubit information. So if it is like a superconducting, a spin qubit, a calibration scheme, and all of these gets fed into the control stack. And there's usually two main things that the control stack does. Basically, sending information as to how to control the qubits applied gates, and also retrieve information back. And also sort of like process the information to make sure that if it's a superconducting qubit, that you get like a 1 or a 0. So all of that happens inside the control stack, but as you can see, it's also the interface to an external decoder. So if you have, for example, like your rerolling box, there's information that goes back and forth from the control stack to your rerolling box. And if you're doing something like a GPU, some tight interconnection with your HPC cluster with your classical sort of like computer processor, there's also information that needs to go back and forth.
If you were doing an error-corrected FTQC, would the pink lines between the control and the GPU be going through the river lane box instead to the control?
Well, this depends because you could do decoding FPGA based or GPU based. I have here the decoder as FPGA mostly because that's what you guys do here at Operate. Like you have the Riverlane box, but you could also see these fitting into more like a global QEC scheme where you have the information going to the QPU, to a CPU, GPU kind of thing.
But I'm guessing, so you're only showing it where you could have interactions with the control plane, not everything in the box that could be connecting each other. Because I guess my point is your Riverlane device there would also potentially connect to the GPUs.
Yeah, or
It's just not through.
like if you were to do QEC and calibration, then you also need to connect like sort of the two decoder and like CPU GPU process.
And but that flow would go down to the control stack.
Yeah.
Through the Riverlane. Yes.
So if you were doing decoding, for example, all of the information that you get out of the decoder gets fed back into the processor that lives inside the control stack.
I see. And then that would go back out to the
and then that will
GPU.
Go.
Okay.
And of course,
would you be able to repeat that? I don't think I heard, I was able to hear everything.
Yeah,
so if you could, yeah, thank you.
I was asking if you see the pink lines between the control and the GPUs, if you were doing like error correction, would you have that pink line also go through the river lane stack there that's in the green, would there be a pink line? And Andrea was basically indicating that that would go as it goes through the river lane device, it would go back kind of around into the control plane, the control layer, and then into the pink layer, the stack. So it's not, it would feed back into the control.
You could also have like perhaps this green box or like this green part living inside like a GPU or like a classical cluster and not having like an FPGA based solution at all. So this is very high level, and I know that if it's not super conducting sort of like spin, it might look very different. The idea with this diagram was to show you that again, we're not just like a black box. There's a lot of things that you have considered, information going in and out in all of the different interfaces. So here you have a problem where you're orchestrating FPGAs, CPUs, GPUs, information at different, I guess, throughputs, latencies, bandwidths, and that is a problem that I think should be solved within the software architecture ecosystem.
So I have a question along the lines of what Aaron was saying. So the pink lines, they go from the processor to the, I guess, the GPU type of thing, right? And then they go up and back into the processor again, not the control plane. Is there a reason for the difference between the workflow in the pink versus the green? Like why is that green going? Sorry, so I'll just walk up here. So this guy, you have the pink line going up here, going into the compute, then coming up and then going back into this guy right here, right? But here it's going.
But that's basically the reason why we also have like this sort of like insert where if you're working at the logical level, you have your circuit that you want to run, but you also have to convert it into a circuit that actually gets run. So what this processor does inside the control stack is basically comes up with like a schedule of like the pulses and the timing between the pulses. So if you get feedback from your decoder, you need to go all the way back because you need to recompile your pulses in time.
And you don't need to do that if the decoder is running on the GPU?
If the decoder is running the GPU, yes, it's just this particular example. And for an NISQ, ideally, you want to have like a circuit template that you don't have to recompile. You just update the parameters. But for QEC, you do have to go all the way back.
So in both cases, then you have to go, whether it's running on the GPU.
Yes.
But even in the case of, say, riverlane, you don't always have to go back to the processors, right? Riverlane can say, I detected errors, I know how to correct your errors, and then go directly talk to the controller. Would that be a potential path to consider too?
No, I don't think that it's the case. And the reason is because it changes the structure of your circuit that you're running. So basically, what the control processor like runs, it's like a schedule of like pulses and timing. And this changes every time you have to run a new circuit based on your decoding scheme.
So I guess like a related question is, right, so so is this classical computing for the decoding, right? So is this taking place in the HPC nodes, or is it taking place in this rack of GPUs, maybe CPUs and FPGAs, which is sitting at the same layer as the control electronics?
Again, that depends on your solution. Like Riverlane does it at the FPGA level.
Say, like I want to run like ML decoder, right? So in that case, do you envision this ML decoder being run at the same layer as the control electronics, or at a higher level where it's running on the HPC nodes, which could potentially be co-located, but it doesn't have the same latency as the control electronics, right? It has to pass through an additional layer to do this compute for the real-time decoding?
So I think that's potentially something to look into in the future, and that's actually one of the points that I have to think about for the discussion. So if we are actually smart about how we allocate resources, we perhaps don't even need like a fast latency for some of the tasks that are, or the information that is shared between the control stack in your classical either GPU, CPU, or FPGA based on your engineering design.
Sorry, I didn't fully
this is-
understand. Yeah, your voice was breaking. Could you say that again, Andrea, please?
Okay.
Fast latency.
Taking a step back. So the
Yeah.
idea with showing you this diagram is just one of the, I guess, early prototypes of like how to do real-time decoding. There are many pieces, many knobs that we can turn and tweak to make this a better process.
Right.
And of course, this is not comprehensive of like all architectures, all of like decoding schemes. I know that people are thinking about different ways of doing this. Of course,
Yeah.
this looks different for something that is not superconducting, but it's just like to set the baseline for the discussion.
Yeah. Yeah. So in this baseline, right? So what you imagine is like, you have this CPU GPU rack that is running the real-time decoding, right? At the same layer as the control electronics. Is that what's going on in this baseline model?
So when you say the same layer, what do you mean by same layer?
So by same layer, what I mean is, right, they're sitting like right next to the control electronics rather than in like, the HPC nodes, right, for which the latency would be higher, right, as opposed to like if they are sitting right next to the control electronics, the latency would be much lower.
Correct, that's the idea with this
Okay.
baseline in particular.
Okay, thank you. Yeah, makes sense. Thank you.
So,
And just to follow up, oh, sorry, Amir?
So go ahead, please.
Thank you. Hopefully, this is a quick follow-up to Gaurav. When you say latency, are you talking about the interconnect latency?
Yes, I'm talking about the
Okay.
interconnect latency.
Right.
Yep.
Okay, thank you.
Mhm.
Go ahead,
So
Amir.
Santiago has a question.
so more than a question, it's something that this diagram seems to tell immediately is that there are maybe distinctions that are worth making in the future discussion. One of them is aspects that will be universal versus aspects that will be specific to qubit species. The second part that would be interesting to try to understand is which of these components is more compute intensive and which one is more data intensive, because that determines the need for buffering, that determines the need to have different types of interconnect, and maybe that also suggests places where not a lot of, or with, let's say, less expensive components are needed versus more expensive workloads components. But it seems to me that locality of data and locality of computation may be a good place to start tracing lines and componentizing based on what goes through which interfaces.
That is the baseline for discussion.
So just to kind of follow up on this, are you asking what's the input output or
Exactly.
in this diagram, what's going into the control electronics box and what's coming out of the control electronic box?
Exactly. And which one of those subcomponents looks more like a simple computation with a lot of data inputs versus a small data, long computation? So things that look more like signals, things that look more like inputs, outputs.
And
Yeah,
I
so
think,
sorry, just
yeah, sorry. In addition to that, I think a topology would be important to understand and help set the context or scope too. For example, are we envisioning one-to-one mapping between a controller and a QPU, chip device? Or are we envisioning one-to-N, N-to-M? So these could also impact the rest of the QEC, HPC stack as well. And of course, firmware that runs on top of that to orchestrate.
Yeah, I completely agree. Like, again, this was just a baseline, but nothing stops you from having an interconnect to two different like GPU clusters, like one for decoding and one for calibration, for example. So it's sort of like choose your architecture for your like specific application. But I think there's still like some common ground that we can agree on, at least within the openQSE discussion.
So if I understood Yasuko's question, the question was, or at least what I heard, is it that you can have one control electronic per QPU or multiple, like can a control electronic rack control only one QPU or can it control multiple QPUs? Is that what you're asking, Yasuko, or did I just misunderstand?
No, that's exactly right, Amir. I ask because that could also, so let's say it's 1 to n to make it simpler. So, you know, let's see, n in this case could be multiple QPUs to a single controller. But maybe a more interesting case is n to m. You have multiple QPUs and multiple controllers. Maybe in that case, you might want to have some kind of orchestration between those multiple controllers. So that adds extra layer on top of that. And so whether the QEC or applications layer, have to coordinate through some centralized controller, box, or, how does it look like?
But do all of these QPUs act as one computer, so to say, or are these just sort of a bunch of computers? Because then I'd say the argument, I mean, it would be like considering a cluster of GPUs where the orchestration is sort of happening on a higher level. Whereas when I talk about control electronics, this sits right on top of the QPU. So that would only make sense to me if this whole thingy is seen from the outside just as one quantum computer thing. Then it makes sense to talk about an orchestration at that low level. Otherwise, this is deferred to some workload manager on a higher level.
Maybe I think the argument here is that as we move to FTQC, we might need to update that view, the sense of how the control makes right in need of more resources as we go into more complex codes or more complex, larger numbers of qubits. So it's one question is, do the boundaries that we know work? Okay, it doesn't seem to be that evident.
Yeah, but then if you talk about fault tolerance, really the view is multiple sort of smaller chips controlled by multiple control electronics, but this is exposed as one computer, so to say. I really need all timing constraints and so on be handled by the control electronic. Okay, yeah. I agree that this needs to be handled.
So there's another element here that probably is not as visible, which is synchronization and coordination. Synchronization and coordination aspect of control. So there is modularity right to each one of those subsystems.
Yeah, I think there's two kind of qubit levels, right? There's the physical qubit level and there's the logical qubit level. And the control electronics can for sure you can for sure access the physical qubit level, and then the logical qubit level is above the quantum error correction. But maybe that's only the point to say, that's the point to say that's where the qubit starts, so to say, or that's where you can interface with the qubit. And the rest is of course below, and there's some information that might have to flow up from there. But a lot of it can also just be contained below that.
So I think now I understand Jessica's question more. Is the question more like if we can treat control stack as a GPU cluster where you can like distribute information among like different pieces, or if we are treating it as a one sort of like compute node? Was that the question? So we just try to like wrap up this discussion about like topology and like.
I think it boils down more to that thinking about addressing one control system is not enough, but you need one more coordinating entity between controller electronics. If, for example, your Q-block system, right, at the moment it has, I don't know, 4 outputs and it can control so many physical qubits. So I need, I don't know, 10 of them, let's say, and all 10 of these need to work in sync to steer the whole computation actually.
So what you're saying is we need to make that distinction of like some sort of like instruction that goes to the control stack, and then from the control stack, how you partition those tasks within the different controls.
Yes, so I mentioned that
I see.
so if you have one control device, it has an FPGA, right? And FPGA has limited memory of how many operations it can queue and store, but that will not suffice to address all of the qubits I have. So I have multiple of these, and if I come from upstairs, I need to divide my program across these FPGAs and need to make sure that everything works in sync still. So
there is a good example. If you have a modular superconducting architecture connected by couplers externally in modules, you have to have one controller per each one of the modules, but you still have to have signals that coordinate the robotics of ensuring that the operations are coordinated at the same time in the same modules.
But I was also going to add, wouldn't that be the responsibility of the compiler to help like abstract that away from the lower level control system?
I'm not sure about that, to be honest, because this needs real sort of real-time timestamps. This needs to be really exact, and I don't think that this is necessarily a software job anymore.
Yeah, and because what I was going to propose is it might be an input to the compiler to at least provide those hints, because I think like who's going to provide those hints? That's what I was actually going to say too, is that like, because are you on a system with a single QPU or are you on a system with 5 QPUs? Is that a responsibility of the compiler, or is that our responsibility to kind of like, that's just a open, I don't know if we're tracking it somewhere.
I think, so for me, the most sense would make if the control stack proposes an ISA, which takes care of that. And the compiler only targets that ISA, and everything which comes after the ISA is hard-coded in the control stack. So all the timing is done then behind in hardware.
So even within superconducting, where the architecture is quite different, right? So how dependent is that on different types of architectures? Because you were mentioning out-of-plane couplers, right? But so for IBM, out-of-plane couplers are quite different from couplers for like IQ, right?
And that's actually what I was thinking, is because it's like with the different modalities, this is going to look very different. So it's like, what's the best way to kind of draw that layer of abstraction is what I'm just not sure.
Maybe what this is, we need something that is control between control and compilation. There's literally a runtime that makes those decisions and works on the partitioning problem.
Yeah.
And then the control system, the control ISA should be exposed to that execution layer. And the connection of, let's say, executing on one particular gate becomes a much more fleshed out program within the language of the runtime. Then that can be optimized itself within its own level, but it is not exactly compilation. That is real-time hardware synthesis.
Yeah, I also think so. Sorry. I was gonna say, I also think so. You basically need a real-time host on top of your real-time controllers to make sure that if you have a set of physical qubits and logical qubits later, that you basically control them still all. You can still do all the error correction and all the maybe real-time calibration that you like to do below that. But then you can, if you bring that together in a host, then you can basically communicate any algorithm execution through that. But yeah, I think that's also what you mean with having the ISA there, right?
Yeah.
So I feel maybe we're talking about two different things, right? There is the idea of you have one QPU that could be partitioned underneath, but it's meant to be one QPU with many, many qubits. And then you have some like a rack of control electronics controlling that many qubits, right? But then there's the other thing that Josh was talking about, where you have multiple differently physical QPUs that are not interconnected at all, right? And then do you want one control electronic rack controlling them and then you're allocating those control? That doesn't seem to be making much sense at that point, right?
This is what I meant at the beginning, right?
Yeah.
This is something a workload manager in the HPC cluster should take care of.
Yeah, but I don't think you would be allocating like a control electronics box
No,
to
but-
a QPU.
Yeah, no,
right?
but each of them has their own.
Yes, yeah.
That's the thing.
So is that rhyming with what you said though?
Yes, what I meant is that in some cases, when we have modular quantum architectures that still live within the realm of a single QPU,
Okay.
because you need fast operations, you still need to have physical partitioning because of manufacturing limits or.
So now you're thinking in the case when we actually have entanglement across. Okay, so now we're not talking classical connections.
Right, exactly. You have to have quantum states
Yeah.
with real entanglement distributed across multiple chips at once.
Yeah, then you definitely need timing.
And I'll also just, I speculate as we continue to scale with number of qubits, one of the things we'll see, and I'll compare this to the classical world for just a moment, is think when multi-core processors came out, just how much that broke the world. And that I think you're actually going to start to see the concept of kind of a hybrid of what you're just talking about, Amir, of that I think you may start to see some modalities that will actually, they'll kind of look more like a multi-core architecture where it would be multiple QPUs all resided within, from one layer of abstraction, it is a single computer, but in reality, it's actually 4 quantum computers sitting next to each other, just kind of poorly stitched together, like very early multi-core CMOS processors.
Well,
That's
the
kind of-
phases will definitely have a different like fidelity between the different.
Totally, yeah. But it's like, I just say that because I've seen a modality that where they divided it up, that basically it was a system that was let's just say 100 qubits for easy rounding. But when you got down to the control system, it was actually representing itself as 2 systems with 50 qubits, even though physically it was doing everything in 100 qubits.
And that's exactly the kind of distributed computing scenario that I was talking about earlier. In that case, they appear, one QPU or one quantum, but under the hood, you have multiple different physically separate chips. So how many controllers do you need? If there are multiple, do they need to I think Santiago maybe excellent comment about coordination and synchronization. Do we need something like that on top of those multiple controllers working toward, logically one quantum?
I think following your comment, that also indicates we need to figure out how much autonomy each level and each component needs to have to take care of the responsibilities that it needs to accomplish. For example, we think about that coordination. Coordination is mostly about sending very small payloads that correspond to signals saying I am ready or I am not ready or this needs to happen. And then it means we do need to define what real time, near real time, and not real time means. For computation time, we should have good definitions.
One just idea I'll throw against the wall of like, do we as an industry have even just like and I will say very lightweight spec. And what I'm thinking is like a JSON that is standard across all of us that discusses this information. Because that might like be a good just initial, like, I mean, I know it sounds insanely basic, but aligning on just like a JSON or YAML, I don't really care about the format. That is just like, I'm this modality of a computer, I have this many qubits. The qubits are either, let's say 101 thing, or it's like actually 2 QPUs with 50 each, like just almost like a manifest file, which I know is this duplicative of QDMI? And I apologize if it is. Because I think that just having something to communicate between the control systems are just like, what am I even looking at? Just a standard might help out, but.
I mean, what we tried to achieve with the QDMI is that you can query the device for such information, and it exposes this in a standard, I think, JSON file, but I'm not sure about the exact format. But there's standardized. So from QDMI side, there's a standardized way to expose that information. But having said that, not every vendor exposes the same kind of information. That's a bit difficult.
It would be nice to have such information, but I don't think we will get much information besides like the national lab solutions.
Yeah, that's been an evolving thing with vendors. Each vendor has different levels of willingness to meet our needs. But for example, one thing I asked metadata was, if it's, give me a Qiskit version and the metadata so that I can because that's in order to compare apples to apples and oranges. If we don't have that, I can't, So I think we probably need to begin, I think that goes into the standards of the a forward-thinking metadata, so that we can,
And I'm even just, I'm thinking basic for our version 1 spec of truly what are the 4 or 5 things. And effectively I would, I don't know, maybe I'm too draconian, but the second it runs into the compiler, if that file's not passed, straight up error, I don't know what to do here. I can't proceed. I have to have that. Might be a gentle forcing function to get compliance. So
I really think that,
So I think the equivalent thing on the classical side is something like HWLock, which enables you to query the topology of the classical system, sockets, cores, threads, right? All that kind of stuff. That seems to be what you guys are talking about. And we have actually taken that and fed QDMI data and HWLock data together in a common graph structure where you have now for hybrid systems really this common representation, and that ends up being a graph or tree structure actually in the static sense with some dynamic information with a graph cut through, right? But I think that's kind of the thing we can play on because HWLock has done this for the classical systems.
yeah, thanks, Martin. That's exactly, I forgot the name of it. That's exactly kind of what I was thinking.
It is HWLock,
Yeah.
HWLOC. And then that we have taken information, we have done a library called syssage, SYS-SAGE, which takes HWLock, which creates, and plus QDMI information, creates a merge tree that can represent, if you get the information, if QDMI is enabled to export this information to get a hybrid tree, which has both the classical and the quantum set represented in one. And then you can query that, you can manipulate that. But at the end, it's somehow extracting that tree.
Okay. What kind of information is there actually exported? Because is it information like how many cores do you have? How much multi-threading can I do? Or is it really like the physical floor plan of the thingy? Because in quantum, from Josh's answer is a bit. I don't think in the future people will say sort of these are the qubit connections, right? But there might be something like this is a compute zone, this is a memory zone. So I'm just, what is the abstraction here? Maybe it's this what I want to know.
I mean, when we did this at this point, it was still the topology of the chip because that's the only thing that was important at that time, right? I mean, you're right. Going forward, that will become perhaps more complex, and we have more different types, and these zones are perhaps a very good abstraction at that point. And you can probably dive into the zones then and have in the zones a coupling map again, right?
So
I think we will have again a hierarchy. Perhaps the hierarchy gets steeper with that.
Yeah.
That's why in classical computing we have a distinction between computer organization, which is the organization into components and modules that have signals and perform single functions. Then we have control units that do exactly that, scheduling, routing, and switching. And then we have the architecture, which is the floor plan, but with the arrows and the timings of the arrows. Yeah.
Yep.
So maybe I missed something. How does that relate to the initial question of?
Well, because it's like, what do you want to expose from the control? Because if you, there's information that is intrinsic to the qubit, but then there's information that is also following up on Santiago's comment. There is intrinsic to the control stack. So for example, as we scale up, you can imagine having multiple racks. So you also need to take into account the interconnect between the different racks. So if you want to entangle qubit number 1 with qubit number n, it might be that it's controlled by one stack, but if you have a tower, it's connected to the other tower. So you also have to expose that sort of
coordinate the qubits.
So we're gonna get into the affinity thing with GPUs and memory and stuff like that.
That changes from vendor to vendor. So that's what they're saying.
We have a big way to say QSPs.
I'd say information like that should be not. I mean, I really think this will boil down to some kind of ISA, right? Where underneath, the details underneath are just hidden. So you will maybe for the next 2 years, people will expose stuff like that, but afterwards there's so many qubits that you don't want to expose to the compiler qubit 1 to 100,000, but you will expose something like, okay, these are the instructions you could do. You could allocate memory, and then afterwards it's hard-coded where this memory actually is allocated. And this happens on a chip system underneath, but maybe that's just my view.
It is important to get to that point, because then it means we have to design components autonomously. Let's take one more example, and I'll shut up on the same.
Please don't.
So let's say you want to add two numbers on a standard microprocessor. There's a mic program, or there's a wired control unit that opens and closes all the channels, all the wires. Let's say there's a wire that goes into the arithmetic logic unit. And if there is let's say somebody or a division operation, and if you divide by zero, what you get is a signal saying, no, you can't do that. And the only piece of information, you don't get any of the remainder weird state of the bits that it may be. You only get one bit back saying, in the program status word, in a special register saying, nope, somebody tried to divide by zero. What's wrong? Maybe those little bits of information is things that we need to understand what they are when we have a control system that starts blowing up in complexity. Minimum information with maximum impact. That's at hand.
So if we go back to, oh, sorry, go ahead.
I was just gonna say, with regards to the comment about the opacity, like there being a point at which, kind of once it gets large enough, I'm not making any assertions, but I'm curious about how, given the nature of it, not to focus on the workflow stuff here, but given the nature of how the limited number of algorithm primitives that are possible, how this would feed back into that, how if you create that level of opacity, this might be a field where you can't do that, right? Where because of the nature of the dramatically varying, kind of organizational hierarchy of the different types of algorithm primitives you're doing, that might kill someone. That might become a very prohibitive layer.
I really don't think so, because it's just for with that. It's a bit where does the compiler end and where does the hardware start, so to say.
But I would need to see some validation. That's what I would kind of want.
Yeah.
I need to show you things, but essentially, if you look at most of the use cases, one can derive a few super algorithms that if you turn certain knobs on and off, give you the standard quantum algorithms that we know. There are a few classes that can be derived from a very large instance. So that's why we have, for example, in standard classical computing, instruction level parallelism, because you can take a large instruction and you can split it into individual stages. At some point, we will need to do that. And to do that, we need to turn on and off components of larger quantum algorithms to obtain the ones that we have. That is possible.
It's a general question. So since some of the information is proprietary and hardware specific, I'm just wondering how much of this kind of discussion is happening on the vendor side.
Do you want the vendor response or like the openQSE question?
Preferably both.
I guess from the vendor perspective, at Qblocks, we try to be as open source as possible. Like our assembly language is like open source. Most of the tools that we build in terms of like connecting to the upper layers of the stack are also open source. The decoder that we're working with at Riverlane is also open source. So that's our motivation for being part of this discussion. Other vendors, I cannot speak to them. I'm not sure that they share this vision. from the national lab, I guess, perspective, there are two sort of like efforts, one at Fermilab and one at Berkeley, where they have very robust solutions. And of course, everything they do is open source. Like they work closely with AMD to develop like all the software layers around them. So that's sort of like the method perspective. From the openQSE perspective, I think it will be useful to come up with some sort of like abstraction, some layer that we can connect to QBMI, where we can ask vendors if you want to be part of like this initiative of like being able to plug into the different pieces of the ecosystem. Maybe this is where you have to meet us. And that's sort of like.
From my understanding, is that would make their life easier, not harder. They're more open to this kind of discussions.
I think there's the sensitivity though from all the vendors is that when you open up certain parts of the control stack, you give visibility into a lot of the underlying information of their system. And there's secret sauce in terms of things like calibration, noise models, things that really characterize the underlying technology. And that can become very sensitive from a competitive perspective with other people working in these modalities. So there is, I think, even outside of the control vendors, many of the hardware vendors themselves build their own proprietary, control stacks, right?
But you can
because of these kind of sensitivities.
But you can still probably have some kind of NDA with the national lab, right? Or something like that.
NDAs you don't put an NDA around special sauce. You don't even patent, it's trade secrets. So that's the problem of being in that layer of the stack is they don't want to even let people know what going on in the stack for a lot of things. And that's why there's so much diversity in this area, because everybody has their own way of building that part. So that's one of the unique challenges. Is it really does get down. You don't have a qubit until you have control.
I completely agree with that notion, and that's some of the challenges we are seeing as well. I'm sorry, I feel like I'm speaking over someone. Oh, go ahead.
No, you go ahead, please.
Oh, okay, thank you. So sorry, I don't think the mic is picking up everything, so I apologize if I was speaking over someone. Yeah, so I completely agree with the fragmentation caused by secret source, and it's a competitive area, so it's understandable. So the question I keep coming back to is that what's the value prop of having open control software, firmware? What does it get you? Why would competitive companies would want to participate in this? I think someone talked about, AMD's effort with Fermilab and Berkeley around creating a kit. It's an open control customizable kit. There, we have a really nice Python-based Jupyter Notebook, software too, and that's really useful to enable researchers and experimentalists. But it was but it's not really meant to be. So the goal there is to enable researchers, not to create competitive products. That was the number one goal. Having said that, you can still create products on top of that. But so I think the question I would like to understand is the value prop.
I'd say in a world where everybody can solve their problems on their own, I would never expose anything like that at all and just do it on my own. But I also think that many hardware vendors, at least in the back of their mind, if they are honest to themselves and look into the mirror, they are faced with the problem that they might not come up with the best solution on their own, just because it is a money game, it is a scale game, it's a brain game, and a community together is smarter than just any vendor of themselves. And for example, IQM, in their talk, they explicitly said they open up their heterogeneous systems just on that level of control, where you can do your own error correction experiments. But that you get control down to the control electronics. So I think there is an incentive, even from the hardware vendors, to open up their whole stack, just to get the most out of their hardware and build on top of that at the moment. And that might change in 15 years, maybe. But I think at the moment there is a real need for that kind of control from the community and have some engagement there.
I think in the 15 years, though, it would also be that I would imagine there would be some standards that would emerge in order to gain the performance and the ability to do all the real-time aspects that you're going to need to kind of be pushing down those open standards to a base layer that people can work on as a vendor to get to that integration point. And so from an openQSE perspective, at least from the way I see it, is what would that be, that kind of base layer that if we focus on the challenges above that in terms of the open source as a community, there would be value for people to adopt that standard and people to move to that standard and people to innovate around that standard to face and address those challenges together, as opposed to maybe some of the more underlying. And so it's like, you know, this is maybe an idealized for someone who doesn't really understand the control stack, but that's how I've been thinking about it in terms of, is there kind of a more like a lower standard by which the vendors would get to, and then they would be happy to embrace things open above that. Whereas right now, because these things expose so much of their hardware, they're less likely to participate in those.
But is that is that standard just your Q1 ASM? So what's the difference between the standard that Aaron is talking about and Q1 ASM as a ISA that you compile down to?
Well, I think it all comes down to enabling adoption. Like our assembly language is open source, but it's like a machine sort of like language, not something that you're gonna sit down and write. So if we could come up with some, I guess, way to be able to plug in easily to whatever the Munich folks are doing, or whatever HP is, or to whatever Oak Ridge is doing, that as a vendor company allows us to enable adoption.
So not to bring on the other guys, but like if Quantum Machines, for example, has this, what do you call the language? Well, yeah. Is that something, is that what you're talking about, or are you talking about something else?
So from my point of view, I agree with you. And the standard should be, now, just as a rough equivalence, it should be something like RISC, right? RISC-V is a low-level instruction set architecture. And if I have a RISC-V chip, I'm compatible with that standard. But what happens underneath it, I don't know. It's my vendor-specific thingy. And to the point of usability, I totally agree that it should be usable, right? But on the other hand, we need to keep in mind that this is low-level system software, which by definition is not easy. That's the hard thing to do.
You're getting into the hardware.
Yes, exactly. That is the hardest part to do.
Yeah.
And people who want to do it need to go down that route and be prepared to do it.
Well, my point was not to make it easy so that everyone can use it. I mean, I think the purpose of like working at the control level later is that you expose down to the metal so you can use like HPC resources to orchestrate over those things.
Mm-hmm.
My point being, like, if we are like a quantum control company, as you mentioned, it's gonna be really hard for us to like build the entire software layer. And then we build it, and who's gonna use it? Like, are we gonna cater to superconductor vendors, or we're gonna?
In Laura's speak, it's to enable the bare metal heads.
Yeah, exactly.
So it also means that as the system scales, some of the assumptions, and as the technology matures, some of those features will not need to be exposed anymore. So it seems to be work for those kinds of standards of saying what is exposed and who consumes it. And at some point having a guard saying, when should this standard fall out of compliance? Because we are at a point where there's enough stability that the community has reached this point.
Yeah,
Why
I
would
fully
the
agree.
crush standard fall out though? I don't understand.
So for example, if there's a point in which there's common understanding and it becomes or there's a de facto standard that solves the problem, that is the de facto standard by virtue of the maturity of the technology. It means that there is a solved problem. Right now, we need these kinds of interconnections because in building the FTQC systems, we need that exposure to make sure that what is being delivered may be validated or is functionally correct. So that is also part of the solution.
So in the morning session, we talked about, in terms of thinking about the boundaries and establishing those interfaces. We would look at what's currently existing and do a few of these kind of use cases and analysis around those to kind of establish those boundaries and interfaces, to communicate between them. But also create kind of a system for learning, for experimentation, to help define where those boundaries should be and what those interfaces should be so we can converge to a standard. So if we think about it in that process, what would the experiments be? What would we need to learn? What would we need to enable in terms of interfaces to experiment with so we learn the most and get to a standard that can then be stable? So,
I think,
yeah.
wanted to say something as well.
Yeah.
On that.
Oh yeah, yeah. So I wanted to say, like, when I think now about the physical qubits and the logical qubits, and below the physical qubits, there's Q1ism, right? So I'm also working at Qblock, so I can speak from the vendor perspective a little bit. Like, the moment we have logical qubits and everyone knows what the ideal error correction code is and how to calibrate, I think we're not going to care anymore. You're just going to make a compiler to the logical qubits, and you don't care anymore that it's a logical qubit below. We just call it probably still a qubit, and then maybe there's 1,000 or 100 physical qubits underneath, and you don't see them anymore. So I agree that there's going to be different layers, and some of those standards can at some point not be needed anymore because you just don't see it. And I think now we're really a bit at the point of, like, we see some maybe pulse level standards that maybe can be vendor agnostic, but for sure on the physical qubit level, you already have multiple pushes for standards, right? With that, let's say openQSE 3 and etc. So that's how I indeed also look at that. By building and by working together, we'll figure out where those levels are and what the information into those levels and out of that is, basically.
Maybe when I look at these slides, right? So for me, on the left-hand side would be the standards, and on the right-hand side is what they should suffice. And somehow I see like one interface is to the above, so what should the compiler see? And one interface is to the side, I call it, like how do I talk to the decoder, right? And there I'm thinking about something like NV2Link or this, what's the stuff from Riverlane called. So there are already things out there for protocols for, I don't know, RDMA, FPGA to FPGA protocols, stuff like that. I think we should, as openQSE, think about this sideway thingy because it's already occupied by two sort of companies, and maybe we should, as an open community, I have a full openQSE head on, not let that standard be ruled by just like one company, right? But rather have something as a community there. And then the second point I want to make, when I think about I'm a compiler guy, if I think about the interface to the compiler, really we should work out what are the KPIs such an interface should really satisfy. Of course, there is usability, but usability from a user's perspective is a vague requirement. I really want to see worked out how much, I don't know, how large can the program even be I submit to that. So how much throughput do I need to enable via that ISA that everything runs and so on. So really hard requirements. that thingy should satisfy.
So if I understand you correctly, you're also saying that as part of the work to standardize in some way, we need to describe and exemplify units of measurement, elements of the architecture that need to be provided at minimum. For example, the size of this minimal programming environment. That is, and some of those will be probably optional. Some of those will be most likely mandatory to then move into certain kinds of jobs. For example, certain QEC codes will require.
Yeah.
Yeah, that's one of the slides, and I'll go quickly through this because we have 30 minutes, and I really want to leave this session with homework for each one of you because we're all going to be working on this, right? But that was precisely my sort of like vision for coming in today was to pose like scaling up quantum control as a software problem, and I wanted to like contrast like two different modalities. I feel like right now most of the vendors are just throwing like a bunch of GPUs and like this fast interconnects are the problem, but I don't think that's gonna be the only solution. And this is something that we were discussing in some other venues. Of course, you're gonna need both, right? But for some cases, can we be smarter about how we allocate like these resources? So just as an example for like the QEC logical level, like of course you're gonna have to need like this fast interconnect for doing real-time decoding, but there are some things that you can do, some like smart ways of doing like lattice surgery that can be taken care from like the software perspective, so that you don't just send like raw data back and forth, but you actually just share like high level information. So that's what I wanted to try to convince you, but it looks like we're all on the same level on.
I'm not on the same level, sorry. If we go back to the, I'm being honest, man. Yeah, I didn't quite understand the idea that you don't, yeah, from what I understood, you're saying that you don't really need that fast interconnect to the outside world. You can do a lot of that error decoding within the quantum, so within the control electronics via some smart compiler.
I'm not saying you don't do it. I'm saying we have to do it smart. Like right now, what most people in like the vendor community are doing is you get like this bunch of information on the GPU and you send it to the GPU and like let the GPU figure out everything. But there are some things like if we are more smart about maybe the control stack pre-process some of the information and then you send pieces of that information or like a summary of that information, and then you send like a smart program that runs all of that instead of like going back and forth. That to me is a software problem. So the hardware is capable of doing that. You just have to be smart about how you orchestrate that.
So data locality
But then
at the
it comes back
control stack.
to be that smart. You really need to map out like where this information flow, what are the bandwidth latency needs for all of these different tasks.
Would it make sense though? Would it make sense to define, because we started looking at the diagram at the beginning, but we didn't really define what the inputs are and what the outputs are.
And that is milestone number one.
Andrea, then won't each of those be platform and vendor specific, kind of at the final level?
Yeah, I was thinking like the first milestone is to actually look at like all of the vendors that are part of like openQSE, if they're open to like share that information. So one of like the software interfaces like currently, what are the latency bandwidths, like how you transfer information in and out from the QPU to sort of like inform those decisions. Because then the milestone two would be actually to use that information to start setting boundaries. Like if we wanted to have like this interface that would be like common, at least for the openQSE architecture, like how this information fits into where we draw the line. And of course, how we interface with the compiler. And then, of course, if openQSE could vouch for having like a real hardware implementation, that would be great.
So is the idea that in terms of that hardware implementation that we would need to work to build like an open control stack, like hardware stack to run this on?
Well, you guys have quantum control boxes sitting around?
I don't think we have any sitting around right now.
That can change. So.
Out of my control, really. I don't have any saying anything of this sort.
I heard Gina that she's fully supportive of you.
Of me. I think you're putting too much words into her mouth right now.
She seemed very supportive when she was talking earlier today of the openQSE effort. So I guess my question is, in order to, if we were to have an open software stack, what hardware would it run on? And what would that hardware need to be? And do we need to define a open hardware stack for the open software stack to run on? That's kind of my question.
So I think outside of openQSE, like there's the QEC quantum testbed. So the goal is to actually have like several like control stacks in like the Riverlane box and like interface with IQM. So to me, this is like the perfect like integration, like you're saying. I'm giving you like the smart software, like they're looking at like the hardware interconnects, like. So to me, this is complementary to what QSE is doing.
But I also think from a hardware point of view, and I'll go back just to pulling my classical history hat on, I kind of like would compare it to like, I don't know if we need a full-blown hardware spec, but I think I would compare it to almost like ATX, if those of you that are familiar with that, of that like, it wasn't really a spec that told you that you have, like, all it specified was that you had like a processor, the processor had memory, it connected to hard drives, and like just things were kind of laid out, but it didn't really go in deep into like, as an example, like it still applies to every computer today, but it didn't say that you had to use SRAM versus DDR. So like it kind of like get hand wavy. Just throwing that out there because I kind of feel like we can maybe pull some analogies of that. I think we could do a hardware spec that's like a very lightweight one, but then still allows the full flexibility of all the modalities, because like a superconducting computer, you can have very different needs than a trapped ion. Just thinking out loud.
We can call it openQSP.
What's that stand for?
Like a DSP, but a QSP.
Oh, there you go. I was going to say QTX, but no.
We could call it the refinable open architecture, not the hand-wavy open architecture.
Exactly, yes, yeah. But I mean like broad brush strokes, I guess the better word I meant, of that like you're not like locking down things that it's like are going to have to be open, but.
Okay, maybe I'm the slow guy in the room, but let me ask my question.
For you, because I know that you're going to ask that question. Within the QEC testbed, you don't even need the qubits. Like that's the beauty of working with that, right? You can just use the data that comes out.
But we're talking about standards, and it's not clear to me, and maybe because this area is not my area, so I'm new to it. What are the standards we're talking about here? What are we trying to standardize or formalize? Like, what is it that we're trying to do? So, like, is it the data format that's coming in? Is it a set of APIs? Is it like a Q1 ASM that we're trying to standardize on? What are we trying to do?
At least they can see standardization of terminology. Different vendors are likely going to use different terms, and how they map to the same concepts that we can use them to move forward. Okay. Second, standardization of constraints. What aspects, for example, real time means that you have a strict deadline, and then you fall out of correctness with no possibility of repair. Near time, you hit performance if you don't get the specific deadline that you have in a certain process. And if you go beyond a certain threshold, you hit correctness. These kinds of things, to spell them out directly, and then go back and go, which ones of these components are more sensitive to which of the constraints? And then which APIs are provided so that you use, let's say, a Q-blocks versus a quantum machines. What do they have to, minimal information they have to supply? If they supply more, perfect. Looking at every single interface and starting to spell that out.
But before, isn't a step before that is to actually define what's the input and output of
Yes.
that control
So
stack?
precisely, that's why like I see all of these milestones like being achieved like sequentially, right? Like first we just do like this study of like saying what's out there, like is anyone even interested in this? Like if you have like full stack vendor where you have in-house like control electronics, would there be even interest about this? Like how are they seeing this connection to HPC, to other parts of the ecosystem? And then milestone 2, then that's where you start saying, these are the things that we would like to standardize. I mean, we can come up with a list, but maybe you can only standardize a few of those things.
And
I think in terms of standard, right, for example, at the moment, I think measurement results are just raw binary in the memory of the FPGA. And maybe that's a standard that you say, okay, you always just have that, and then you can build a standardized protocol to access that memory data, and that would be a standard. But maybe it's not the best one. So, but yeah.
Even the exchange formats, for example, I've seen people use CBOR, I've seen people use JSON, I've seen people use raw text to communicate those measurement data. And
In metrics of performance.
And metrics of performance. Yeah.
so that is something we can say, if you want to participate in openQSE at the control level, we expect at least this data format for particular read-out measurement data.
It might be the case that we cannot do it. Like it's just too much at this point in the community, but at least the contribution from openQSE would be to say like, this is what we found and this is why we cannot do it at this point in time.
So just to solidify my understanding there, like the inputs there, the input into the control electronics is usually the circuit that you're going to run, whether it's like FTQC or just NISC, right? Is there any other input there?
Yeah, I mean, that would be an ISA, right? Q1SM is the input to the control electronics.
Okay. And then the output can be the syndrome readouts, right?
Yes.
Or it can be the measurements, and both of them may be the
This is
same.
right? This is the same. These are just measurement data.
Okay, so then there's only one input and one output.
Yeah, but I think what needs to be, at least for the output, what needs to distinguish. All of these are measurement results. I mean, this is the only data I can get from a QPU anyways, right? But some of them needs to be processed in another way. For the syndrome data, this needs to be processed fast, at least for some modalities. You might want to have a different way of handling those. But if I have, I don't know, some feed-forward algorithm, I might be fine with doing something slower. Also, maybe I want to do that fast, but I also think one needs to keep in mind practical boundary conditions like cost of building stuff. Do I want to have the super fast, high expensive stuff for everything? Yeah, maybe not. So maybe I want a different standard for just feed forward thingy, which influences the algorithm, but not the error correction.
And there's also data output in the form of failure modes. For example, if half of your qubits are dead, you might want to know that the control signal needs to tell you, not in gory detail yet, or maybe you have part of the more specialized instructions architecture. For example, if you have an Intel microprocessor, you have the usual instructions to do computation, and you do additional instructions to do performance analysis. So maybe there's an additional part of the ISA that says, okay, I know this QPU failed. Now, the persona that is the quantum systems engineer wants to get in and do something, wants to perform something much more sophisticated. And then they will be able to, okay, if this failed, now I go into hardware mode, hardcore, and I can do what I need to do. But at least the initial information is not overwhelming.
And something simpler, like, is there any configuration tasks that need to be done to the control electronic, like APIs to configure the control electronics in some form, maybe configure the QEC code that's running, something simple like that? That seems to be like the low-hanging fruit. You can just standardize those things because
yes,
you know that you want to configure them in specific ways.
Quantum firmware.
Sure. What's the configuration things that you can configure? That's just my theoretical idea, but what is practical things that you can configure on the hardware? that you would want to configure on the hardware.
So, but I think like stepping back, if I can, something I mentioned a minute ago, like just to throw out there again of like, part of why I mentioned like a very tiny spec is like, I think that might be a good like little gateway just to get a nudge in to start getting the data-driven answer to that question. Because what I mean there is that like, I think once you get that little payload file in the door, like that's the biggest first hurdle. And then you can start, businesses will start seeing they can pass that information around easily. And it's like, oh, why don't I just strap this on there? Why don't I just put this on there? Put a comment field, put a stray data field that literally they can throw whatever they want. Would let you start getting data-driven insight on that question is what I'm proposing.
But we need that initial set of things, right?
And I would literally, what's your modality? How many qubits do you have? That's it.
Calibration data.
What's that?
Calibration data.
Yeah, what's that? Is it calibrated or not calibrated or?
Well, not just, but what are the probabilities? Because that's
Yeah.
some of the information that I'm actually using even before running. Sometimes for the post-processing.
Yeah.
Sometimes even before mapping. So.
Because kind of what I was just proposing is back to Aaron's point of, I think it's going to be a little hard to get, some of the vendors are going to view even some of that information. Like, what's the bare set of information that we should have? Maybe no vendors, maybe one will scream that it's considered like proprietary secret sauce. If like 50% scream, fine, just throw it off the list for now. Don't worry about it. But just what's something so tiny, just to kind of get a ball rolling, just throwing an idea out there.
People like to say number of qubits, so
I would hope not. Yeah. I'm never surprised, so that's why I just say never surprised.
So that would be part of your milestone one, Andrea, like that minimum spec that Josh was talking about.
It could literally just be, I mean, what QDMI is already doing. Like honestly, like that could be the spec, because it could just be what QDMI is already doing. So I'm by no means saying reinvent the wheel, but it's just have a spec that's. Yeah.
Here's an interesting thing. So what QDMI is doing is it's querying, like it has a device driver that is device specific. It calls into the device, get device specific information, and then reformats it into something that is common, right? But what we're talking about here is we actually want to push that commonality below the QDMI. We want whatever comes out of the hardware is already in some form that is common, and then QDMI can just pump it up, right?
Yes.
And what I would even propose, if you want to go a step further, think about telemetry of basically, and this would be on openQSE to figure this out, of like, ask vendors if they would consent to that being just telemetry up for statistical reasons. And all it is just to count how many people are using the spec. And then at that point, like you have a small hook that you're starting to see what are people using this, what companies are using this, what are they doing with it? And then you can start making data-driven movements and just kind of see traction. So that was kind of what I meant, connecting the dots there on that thought. I'm not sure, does QDMI have any form of telemetry right now?
You can.
Yeah.
But telemetry, that is something people always want, but it's a bit hard to get. So it's,
yeah. Sorry, I don't want to rabbit hole in telemetry because that could be a whole other topic. But
I think they're discussing that in the other resource management.
Yeah.
Discussion.
But it's just I do sense there's going to be a little bit of friction from some of the more vertically integrated vendors, just because it's like, what is this doing for me? So it's like, I think just we have to think about like, what can we do that's like the tiniest thing that's going to be just a tiny win for them to keep kind of chipping away at that bias to not use it.
But maybe that's a good question. What is it like if for vertically integrated vendors that you're talking about? What benefit is it for them to go toward the standard?
What can we learn as a community?
Yeah.
And I think if we arrange the work and the milestones around what we can learn as a community, that will allow more buy-in, enable more maturity, and get to a standard interface that they can leverage. I don't think anyone wants to just have a bunch of engineers working on the same problem that everybody's working on. For the sake of IP, stuff that they, not even IP, the secret sauce. If we can get to a layer that the field can kind of standardize to, it reduces the headcount significantly at that layer of the stack, which is a huge OpEx benefit for all the industry.
But I think, Amir, that the spec itself, probably not a lot of value, but where the value comes, we have the spec, one company produces a tiny tool to do some form of analysis on that. Another one builds a telemetry tool that allows you as an individual company just to start querying your own hardware. Another company builds a little tool. This is all just like, because it's all using the common spec.
So the ecosystem that you build around it, it becomes rich enough that companies can leverage the value out of it without.
My theory.
But vertically integrated, that they have no interest in that.
But there's something a bit stronger maybe. The spec like this, I can see it doing some work for validation and verification at the government level that vendors have to satisfy to demonstrate that they have at least components they can register.
It's also where I'm pulling this thought from is, and I'll pull akin to when I worked on validating aviation equipment. The very first thing that happens is they use like, it's effectively the equivalent of RS-232. All it's doing is querying like, what the heck am I plugging into? Oh, okay. I'm talking to a cockpit head unit. Okay, so I know that you're a type of like, you're gonna have glass, you have a heads up display. Like, it's almost just like a manifest file of like, what is going on here? And it's very common even in the CMOS world with automated test equipment to just have like a file that is like a, what the heck are you looking at? Just so that you have an understanding. And that might actually, I kind of like the idea you mentioned testing. That's a whole world that like test vendors will start to pop up in the quantum world. There's already a few of them. And they're going to want an easy way. They're not going to have to know the innards of the quantum computer. They're going to want to just have an easy way to plug in and start looking at things. So
You're envisioning national labs.
yeah,
Oh, test locations.
and kind of like, is it DARPA QBI? Is that the initiative where they're doing testing? Yeah.
Well, benchmark initiative is tracking what's going on.
Because have they selected? I don't know if they've selected their test vendor yet. Have they? I haven't heard.
We're still moving to phase C.
Gotcha. Because I was going to say that whenever that vendor comes, these are all things that I would say they would be a good person to pull in to help advocate for some of this from a test point of view as well.
Any incentive to have a system verifiably correct that the government can buy should move the needle forward. And that can be certified. That for certain environments, that's going to be a requirement, I suspect.
The government could also put it as an insanely strong requirement to the point of it is the requirement in the contract. So as another option.
Side note about testing, seems like there is multiple layers of ways you can test, and you talked to Mark, right? Like there's multiple layers of testing that they can do. They can test at the physical layer, they can test at the logical layers. Is what we're talking about here, can it be tied somehow to that effort?
Yes, because when you speak of testing, there's functional testing and there's also specification-based testing. So having a description of the sort of these interfaces will accelerate how vendors can comply with these regulations. And by providing that the government teams will know what to test, and there's going to be an easier match. Because right now, as far as I understand, it is very bespoke. You have to go deeply into every single thing that is unique per vendor, and that is very painful.
To say if you wanted to run like a variational algorithm, you wanted to try like different things with like something like this software stack, you would say just run it through the stack and then give me, I don't know, whatever metric like latency.
So another question, can this software stack be done in simulation without having to have any real hardware, like to just validate
Yes.
the concepts that we're coming up with? Can run it on a Linux box. We don't have to have a. Well, you said control electronics box. I don't have a control electronics box. I have my desktop. I run it on. Huh? But like what I'm saying is, do we even need the control electron? Can we just run the stuff on just a Linux box?
So we can test the functionality of that description on digital twins. I did build digital twins of superconducting hardware, and it is very easy to go and instrument the twin, which is basically a discrete event simulator with an open quantum system simulator attached to it. And maybe we could also propose there's a digital twin that is also part of the reference architecture if needed. So we simulate something and see if the box that we're analyzing that's real matches some of the signatures, not exactly, of course, the performance, but matches the signatures of the testing.
Do we have that, or do we need to build it?
We might need to build it, but it is not that expensive to build. That's actually, I think Chris Zimmer is thinking about this already.
Thinking about what?
About having a digital twin for the HPC, so QPU, something like that. There's already work, and it's not that complicated to.
And it falls nicely with the intentions. AI.
Wrapping my head around it. I'll have a few questions in a moment.
Maybe from the experimentalist or any one of you, what are pain points that you have identified about cluster since a while ago? Things that would make your life easier.
So, do we have 1 hour and 30 minutes as you said initially, or?
Yeah, but for
Yeah, because the agenda says
In reference to.
4:15, so that's 2 hours instead of 1 hour and 30.
Signals.
you have until 4:15. But probably reserve some time so that
We need to merge.
At the hardware level, it's a lot of like.
so I might want to work together. He's presenting the first session.
What you're saying is that we close the session at 1 hour and 30, so we have 30 minutes to work on the.
Session. Can work on it together.
The host level control under, right.
And you said we didn't have to write a report, that AI was doing it.
Well, it helps. We still have to, we should review what AI tells us.
Okay, sorry for people online. We're trying to figure out if the session is ending because we're supposed to like take everyone's input today and merge it into like a digestible way for like the final report that the boss is doing. So should we spend?
Should be on the Linky segment. Okay.
All right.
Should we spend the last couple of minutes like refining if everyone's okay with like milestones? I had like a draft of like open questions that we could like think about as we walk into like milestones.
Like even just the experiments.
So first, like milestones, is this everything?
Control electronics.
I mean, everyone agrees that is something doable, reasonable within openQSE.
That's.
So the fast feedback, sorry, can
Go back.
So I'm trying to.
Make it editable. Okay.
for the fast feedback protocol definition, is that something like QECI?
Okay, so what I'm thinking here is once we have like these sort of like mapping of like state of the art right now, then we have like the boundary specs. This is sort of like more on the like R&D planning. Like if we were to deploy this and integrate it with like an HPC ecosystem, like what would this look like? Based on the metrics that we define on milestone 1 and 2.
That's milestone 2. You're talking about milestone 2 right now, right?
Yeah. No, milestone 3, like the fast feedback protocol definition.
Yes, so repeat that again. I didn't quite get.
So what I'm thinking for milestone 3 is once we have like all of these boundaries, all of these like definitions, performance metrics, to me, milestone 3 is to actually start building the blueprint of like what this sort of like system would look like if we were to deploy it. So like the step in between like this sort of like white paper discussion and the step before actually deploying it on actual hardware.
It's the interface to the level above, basically. Like you want to define the level within, and then you do the interface above.
And
then you actually build a reference implementation and test it.
Yeah, so it's not clear to me what the reference implementation is. Is that like some hardware component with?
Well, it sounds like you would need to run on the generic control hardware electronics.
Or the digital twin if we build it.
So I have a question about that. Like the work that LPL is doing, because they presented and they said they got an IQM, just a chip, and they integrated their own chandelier and their own control electronics. Is there something that we can collaborate with them on this kind of stuff?
So you're saying AQT?
I don't know.
At a station?
Yeah, is that something possible? Is that not possible? I don't know. Like, I'm just thinking, like, if we bring more people on board.
Well, it seems like that would be part of the comprehensive document cataloging this current state-of-the-art physical and software interfaces. If we want to,
So that
if we want to make use of this, or
In fact, like so Amir is talking, there's some open source sort of like control at Berkeley. And they presented openQSE last Monday, but she wasn't able to join because she's like on PTO. So she's interested in like becoming part of this working group, but just not suited. But yeah, I mean, that's something that we could do. And it's something that makes sense.
It could be both, right? We can be doing two things at the same time. Like, if they already have interest and they have this test bed already created.
don't need to recreate the wheel.
Yeah. And we can, if we already do it locally with Chris Zimmer stuff, we can do it locally as well.
So they have an IQ chip.
That's what they presented. And they connected their own chandelier and they connected their own.
Yeah, AQT has the full.
Yeah. So it was interesting.
I think
One-
there are
one of
two
the
other
things
good
that-
options too.
Yes, yes.
Yeah. So one is check the open quantum control kit coming out from Fermilab. So that's fully customizable with a Python Jupyter notebook-based software wrapper. So that makes it much easier to experiment. The other option is IQM on-site, on-prem, because their control is fully open. So you could, because the system is already there, you can use that to prototype different interfaces too.
But then for IQM, last time I talked to Travis, he said that we cannot open the control box because then it voids the warranty. So I'm not sure how.
I see. Okay, I wasn't aware.
To that level, I'm not sure at what point anything.
I mean, that would be bringing IQM into this conversation.
Yes, exactly. It would.
I'm not aware of any plans of opening the control electronics in IQM, in the system that we have at least.
Maybe, I mean, we're jumping a bit ahead, right? Maybe we try to get as far as possible with just software, which we can do on our own. And then once we really hit the point, we say, okay, now we need to test it, and we cannot test it on some emulator, we open up the conversation to hardware. And hopefully at that point, people have become aware enough of that effort and convinced enough of that effort, they are saying, okay, we want to participate in here. Right? Because if you do it now, I can see hardware vendors just saying, yeah, but what's in for me here? I don't see it at that point. And then they're closing up.
So I have more of a practical question then. If we are planning to do that, how do we, like, what funding pool, like how are we going to get man hours to actually do this, right? Like, who's going to, like, at least on our end, we're working, being paid by OLCF or whatever to do this. So some of the work can come out of that, right? Like, we can do it, but I'm not sure if I have the right skill set to actually get it done. But how, like, the paper, the research and the stuff like that is feasible. But once it gets to reference implementation, who has the skill set, who has the time, who has the funding, who's interested? Like, we don't have to answer those questions now. I'm just saying, like, it could be something that we need to think about. But for the first 3 milestones, seems like this is stuff that we can start on immediately.
So in terms of next steps, how do you want to like set this up?
Our working groups have like regular meetings, so, and for example, in the system architecture one, we meet every Thursday, and Johannes is starting to put the layout of the paper, and people are starting to fill pieces up, so we can do something similar.
So you
Preferably, we do it so that it doesn't overlap with all the other working group meetings. So if someone wants to be on 2 working groups, they can be.
I think there's only Monday and Thursdays right now. So anyhow, there's not.
Tuesdays is the interface. No, that's. We have the QRMI, QDMI.
Oh, right.
Are all these listed in the times on the Confluence somewhere?
Not yet.
Yeah.
Point.
That'd be great.
It would be
Yeah,
nice if someone could-
meetings get listed there.
Shall we also open the Slack? No, there's the openQSE Slack channel, right? We'll open.
Oh, you can have a channel on
Yeah.
there for that particular, for the
Control panel.
the control.
And it would also be nice if we had someone in this group that could attend like the compiler group, so that we're all like seeing.
I think both of you are compiled.
Yeah, I can.
I'm not sure what other working group.
I'm sure Michael would want to be on this as well. Actually, he can't be today since he's leading the compiler.
Yeah, we need to work for. And the other one.
So is there, I guess, since we're not in the compiler group, and maybe you guys were in the morning session, just in terms of the interface from here up to the HPC and here up to the quantum error correction, who is defining those two within openQSE? Is that the compiler or is that another working group?
I'd say we should define the interface to the compiler.
All you're saying all we should do is define an interface to the compiler as the above? Or should we, are there other interfaces? Because I thought off of Andrea's plot, there's a couple external interfaces.
Yeah.
And that's why I was wanting to understand.
I'm not saying we should, this is all we should.
Yes,
I'd say this is.
yes.
Thing we should do.
Yes, that's what I was trying to understand is, and that's why I was asking. I know there's the compiler level, but I'm also wondering if there's not a couple other levels in which we need to also define interfaces.
Yeah.
And that's where I was trying to understand, within openQSE, who are defining those pieces and how would we interface with those? Are there people defining anything at that layer?
Let's try to define the problem a bit more quickly. I imagine such an interface divides the world between what comes up after doing symbolic processing and annotation, that's compiler work. So it crosses the line into the runtime, and that is the moment where we come in and define how it needs to happen. The moment it has to go through that diagram that I represented. But yes, it's final transformed symbolic program plus annotations for execution, given the information.
Because this is a software architecture group, we define it.
Exactly.
Okay, sorry, I had my head squarely on control. I had forgotten where I was. Thank you. So we're defining this in the, not in the control, but in the software architecture.
Someday some parts will become hardware and we can rest assured.
So we were talking earlier about the runtime environment or interfaces, but is all that is contained within that context from your perspective? Because we were talking about what would be just an object, right? But I'm not sure that this stuff that we're talking about would be compiled as an object.
It's more, again, hardware synthesis in the sense that there are programs, but the objective of those programs is not described in a symbolic form that the users care about. It is described in a form that the hardware cares about to know how to execute. and obtain information back to the user. I think there's a fine line dividing those two worlds.
Can we sort of, since also in the interest of time, can we end that meeting with some concrete action items and timelines, at least sort of timeline, not like deadline tomorrow, but until, I don't know, end of the year, we want to have milestone 1, I'd say, something like that.
That makes sense.
So I don't know, we say, we set up, next step is via Slack, we set up a regular meeting, because I think setting this up now, we miss people and their availability. So we make, I don't know, a Moodle with some poll we can in, and we have a regular meeting and make, I don't know, some kind of work structure breakdown for until the end of the year. Does this make sense? That we have such a work structure breakdown, I don't know, in the next couple of weeks.
I have that as action items for myself, but then my next question was, would whatever we come up with this, would it be part of like a larger timeline from openQSE? Like, are you targeting like a paper, something as openQSE?
I would hope so, like that would be milestone 1.
So what is the timeline?
It within the, your question is not just for this project, but we're wrapping it into a much bigger thing within
Yeah,
all of.
so I mean, of course, we can set our timelines, but like, if we say like, oh, we're gonna have it in 2 years, but then openQSE is looking to have things in 6 months.
No, so I think what we, like the aggressive schedule is to say by SC 2027, we have the first version of the specification, right?
2027, not 2026.
Yeah, like SC next year.
Year and a half.
Year and a half from now, right? That would be the first version of the specification, which would include, I guess.
So then that would be milestone, up to milestone number 3. So basically this blueprint of like, if we were to plug in the control stack, whatever generic control stack to the openQSE architecture, this is what it would look like.
Yeah.
So milestone 3 would be SC 27.
Let's shoot for that. Is that's not aggressive? You wanna make it shorter?
Well, it's not really a year and a half either, is it? Because to be at SC 27, you need everything in the spring and summer, so.
Exactly.
You need everything
Yeah.
before.
It's less than a year for the first submission. For workshop submissions, it's a year.
Needs to be by like what, March or April, something like that.
Well.
To submit to SC,
To submit to
you need
SC,
something in
it's
March.
March, April,
Yeah.
and to submit to the workshop. So you can do the full paper or you can do workshop.
Yeah.
So the full papers are March, April. So it depends on the scale. Obviously, fallback is workshop papers are August.
So what I found with SC is submitting paper without some actual like implementation behind it. They really frown upon that.
And we should not do that, right? I mean, I have the strong belief that just another paper will not solve any problem. I'd much rather have a good implementation people can use, delay the paper to eternity. I don't care, to be honest. It should be hands-on and not a debate club here.
We can push updates to IEEE QC. That's an easier part to move forward to if needed for intermediate products or other. But a good publication in the journal takes time, will allow us to mull over.
Is there something we can show for Quantum?
It's quantum.
This is Quantum.
Oh, one thing I was going to say is, I think, we have these technical milestones, but this is openQSE is an open source, open development initiative. And I think we need to, and maybe this is something we could do at IEEE 1 week, try to get out in front and say, look, as a group, this is what we're doing. We want people to be involved in this and try to bring more people into this vision. I think that would be a community milestone.
Venue for that.
That would be very useful to try to, build consensus and build more awareness around this. Because openQSE, even though we all know about it, not everybody knows about it. Josh told me I was the first person that said anything about it in public. So,
mixed feelings about that.
Yeah.
I see the point, but I also feel that if you prematurely open up stuff, it will get crazy and then nothing will come out and people will just drown it into bad code and stuff, and it becomes uncontrollable. That's my personal view.
Well,
and
I'm not saying that we have to open up the GitHub to everybody initially. You know,
Yeah.
maybe there's some controls that we need to put in place, but you know, as the folks who are actually going to participate in the development, we need engineers.
Yeah, sure.
It ain't me, I know that. Like, I'm not going to be coding anything.
Yeah.
That's and there's usually an army of grad students that attend these things, and that's what I'm trying to find is how do we recruit the army to help solve this problem? Because that ultimately we do have a coding challenge in front of us. I don't see any grad students here.
But if you talk grad student, you need to go back to the papers.
Yeah.
Right, the grad student will work for paper.
Yes.
That's also true.
And if we get an army of grad students, there's more likely to get a paper. We have implementation, we have good tests, we get good papers.
Yeah, sure. I'm not saying this is a negative thing, right?
Yeah. So that's the carrot.
Logistically, armies of grad students are very hard dimensional. Sorry.
And I mean, there could also be some milestones around like how we do our engagement with other DOE labs, like Berkeley, you know, the activities, these places that we would maybe be able to get access to other, you know, program funding, people who are working on these things. Yeah. So, I mean, I don't want to open up the doors to Pandora's box, but I do think, you know, from a funding perspective, openQSE is an unfunded program.
Yeah.
From a development perspective, as far as I'm aware, Samir
I
is really good friends with Gina.
I get funded, I get paid, that's about what I know.
That's absolutely true, yeah.
So what did we arrive to? What's the summary of this? I'm slow. What's the milestones now?
AI is generating an output.
You're typing a lot. What are you typing?
Summary is we need funding in the army.
No, so we're gonna open like we're gonna start a regular meeting to start working on milestone 1, right? And milestone 2, I guess, or right?
Yeah, and there's a few people that were interested but were not joining today. So we'll have to
Can you share the Slack as well? Because there are people here
and
today.
open the Slack app. Yeah, open the Slack, send out a Doodle poll to find like kind of thing to set up a meeting, reach out to additional participants, define milestones, timelines.
And maybe we can start looking at milestone 4, but not necessarily implementation wise, like figuring out the tasks that need to occur in order to actually get milestone completed, because this is a big milestone. You probably have a whole bunch of like subtasks that you need to complete, right? So breaking that each milestone up into a set of subtasks that can allow us to, you know, reason about the problem a little bit more fine-grained. There was a break, by the way, you guys missed it, sorry.
No, there was a break, what?
There a break? I thought there was a break.
I'm sure there was a break. We built breaks in every, well, actually, no, your
Oh,
schedule
we just had a
might,
break, is that what that
your
was?
schedule might not have had a break. Oh, no, they must be working lunches and they have to be very confusingly worded, so you don't understand when you're supposed to eat and when you're supposed to work.
As opposed to a networking lunch.
I'm sure you just call it a working lunch with some sort of topic that you can network about. It has to have a topic though. Yes, must be an agenda item for your lunch. Yesterday's was a word networking one. You know, I just made public announcements and stuff like that.
Okay, for the people online, we're closing the session because we need to go prepare a summary for the session, the main session at 4:30.
And we need AI to
They
generate
can
that for
join,
us.
right?
They can join at a 4:30 session.
Yes.
Yeah.
And what link is that?
That will be the Tennessee.
The main one.
Maybe.
It is that on the email that you.
Yeah, I sent the 4 links. It should be there.